So we are currently at the lecture 18, and maybe one lecture hour is behind our schedule. But anyway, we will keep this lecture content. So today we will talk about velocity saturation effect. Okay. Before talking about the velocity saturation effect, first of all, let's finish our previous contents on Schoener effect. So if you remember correctly, so previously we had to solve a system to the Poisson equation, and although that is a Poisson equation, but it has just a constant density Na, and that was actually consumed by our test function called as v of x and y, that is corresponding to the long channel MOS capacitor, and impact of a source and drain. Yes, here we have a source and drain, and that part is taken by left side function and right side function, and those two functions just to take the impact of our source voltage and also drain voltage. So in this case, already the impact of our doping density is taken by this V function. So actual function we must solve for use of L is just Laplace equation, not Poisson equation. The difference between Poisson equation and Laplace equations comes from whether this right hand side of our equation is 0 or not. If this is not 0, non-zero value, then we call it as a Poisson equation, and when this source term, this term becomes 0, then we call it as the Laplace equation. Certainly, we must solve Laplace equation for this left side function and also for our right side function. We must solve these two cases. Okay, so after that, we just made a series expansion on the mismatch in this left side and right side, because our B function just gives us the potential profile corresponding to the MOS system. So it provides us a certain parabolic behavior if we just draw it as a function of a depth scale, and if this is corresponding to the potential, then we will have just a parabola. However, our boundary condition, the required boundary condition fixed by our source potential is just given as this one. So this difference should be taken by our left function and right function. And this one is just decomposed into different sinusoidal functions, like different n values, and we have thought about the lowest one, because if we go to higher order, then actually that will just cancel out to each other, so they do not contribute to our solution. So that is the expansion result shown here. As you can see here, this is corresponding to our V function. So this is the one of our MOS capacitor, and this is corresponding to the source related term, and this one is the drain related term. So now we wanted to calculate our surface potential. How can you calculate the surface potential? Surface potential means that the position, vertical position, should be the one for interface. So we can just insert x equal to 0 case. Then we will have this simple expression. this is a constant value. So as a function of y, we have certain constant value corresponding to our long channel MOS case. After that, depending on our drain voltage and source voltage and drain voltage, we can have additional component that comes from these two sides. For example, here and there, we can have additional value, and this additional value has the dependence on y following hyperbolic sine function, and its length scale is lambda. So if we go 1 lambda, 2 lambda, in this case we can get quite a rapid decrease. For example, if we go just to 1 lambda, then what will happen? Compared with this one, so think about this one. So hyperbolic sine, by its definition, it is just a half of exponential x minus exponential minus x. If we just insert 0 as an argument of this function, then we will get just a number 0. And if we go to number 1, when x equal to 1, then we will get exponential 1, it is exponent, and minus exponential minus 1. This is much smaller than exponential, and that's difference is shown here. If we go to number 2 or 3 for our input argument for this hyperbolic sine function, actually this second term corresponding to minus exponential something, that rapidly converts to number 0. So we will get just a simple expression like this. Hyperbolic sine function just follows exponential x divided by number 2 for x equal to which is much higher than this number 0. Okay, so therefore now we can understand the length scale is more or less given as lambda, or lambda divided by pi. So anyway, if we go a little bit further to this length scale, then that will diminish quite rapidly, and we will have just behavior of a long channel device. Otherwise, we will get certain potential here. So that is the problem. Maybe you can ask me this question: is this solution available only for our VDS equal to 0 volt case? Actually not. Even when we have high drain bias, for example 1 volt, 2 volt, 3 volt, still this solution is valid. Then what happens in this case? Compared with our B1 value, our C1 coefficient will have much higher value, because their approximate form for B1 and B2 is shown here, and depending on our additional drain voltage, our C1 value can be much higher than B1 case. So this is valid for not only for drain equal to 0 volt case, but non-zero drain voltage can be considered in this case. Then now we understand this one. At x equal to 0 as surface, if we draw potential as a function of y, then source side we have a little bit increased value due to impact of source, and also here y equal to L drain end, here we have also a little increase of potential due to the impact of drain voltage and existence of drain side. So from the viewpoint of our electrons, actually this phi, if we have this kind of behavior, actually the most important part would be this point, the lowest one. Why this lowest one is important? Because from this potential we can convert it to like this way. We can make certain values corresponding to this conduction band minimum energy. Of course, we should be a little bit careful. If we wanted to be really rigorous about it, then the actual way we get this EC value should be like this. Just to multiply minus Q to our conventional electrostatic potential. And by taking this number, what is the physical meaning of minus Q times phi? That will represent the energetic position of our intrinsic Fermi level. And for given material, of course, we have given difference between EC and EI level. Everybody understand this number is more or less about half of band gap energy, because for silicon, conduction band and valence band are well matched, and their how can I say, their size are similar, so they can be matched in this case. So that will be the exact form of our EC value. Right now, I'm just saying that minus times Q phi will follow EC. Of course, it is not a correct one. So please think about this one. This is the exact expression. And what is our phi? Currently, we are not using this phi usually used in the most more rigorous context. Instead, we introduce a certain convention in this textbook, like phi plus phi b, that is defined as our potential in this case. So now we have minus phi b to compensate this conversion, and we will get EC minus EI. So simply speaking, if we say this is the potential following our textbook's notation, then we will get some relation like this, EC minus EI. However, anyway, here we have certain number for given system. This phi b, even this phi b is a given number, so they can be regarded as a given constant. So that's the reason why I'm saying that this EC and minus Q times our current value of potential can be regarded as corresponding quantities. So by adding certain numbers, we can easily convert it to the conduction band minimum. So simply speaking, from this curve, we can draw in this way. Still same Y position, and now EC, and this EC can be regarded as following this form. So if we have certain position of having the minimum energy here, then at the same position we can get the maximum value of our conduction band minimum energy. So this minimum value of conduction, maximum value of conduction band minimum can be regarded as the overall energetic barrier for our system. So think about this one. Here we have certain roller coasters, and if our train is initially started from here, then in order to overcome this rail, then we must provide the energy corresponding to this amount of height difference. So if instead of this red rail introduce, for example, this black rail, then what will happen? Actually, the energy which should be supplied from our motor system is increased by amount of this height difference. So simply speaking, this maximum energy of our EC value can be regarded as potential barrier. And as you can see, compared with this, let's say, compared with this long channel value, this is corresponding to long channel approximation. And now our potential value can be increased. It means that actually our maximum value of EC, the overall barrier, can be reduced. So simply speaking, the barrier, the total channel barrier, becomes a lot easier to overcome. So that is the reason why we have much easier current conduction compared with long channel device. So that is increase or decrease of our threshold voltage. So I already explained this one a few times already, but I wanted to repeat it once again. Okay, so therefore, that's the motivation to find out where it is, what is the position for this lowest potential, and what is the value of this potential increase. That is shown here. So please just have a look at it. So how can you find this minimum potential position? That is not that difficult. Just takes certain one like this. This is already x comma y, x equal to 0 and y is position value. And if we take this first derivative with respect to y, then that should be 0, because there is a certain curve, blue curve shown here, and if we wanted to make the extreme value, then of course at this extreme point the first derivative would vanish. So that's the reason why we can just take this simple expression. By taking this expression, and we can find a certain value y, or which y value satisfies this expression, and you can see that there is a certain numbers. Yeah, but point is, think about this one. Well, first of all, as much as this expression is correct, this potential is correct up to this point, this is the exact one. And here we introduce approximate value, because C1 and B1 have their own approximate value or expression. That's the reason why here we have a similarity, not exact equality. But before going to the rightmost term, please have a look at this, the exact number. C1, B1. What is C1 and B1? B1 is corresponding to the source voltage, and C1 is corresponding to the drain voltage. And let's just say that we happen to be, they are the same. It means that we apply the same voltage to source and drain. What is it? VDS equal to 0 case. Then in this case, C1 and B1 will be the same. So this number becomes just 1. And we must take logarithmic, natural logarithmic of number 1. That vanishes. So simply speaking, at 0 drain bias case, our YC value, where we have minimum potential, will be simply given as half of length scale or channel length. That is quite reasonable, because source and drain are biased equally. There is no preference for source, no preference for drain. However, now if we apply positive bias to our drain relative to the source, then C1 value will become higher than B1. So now we can easily understand this ratio, C1 over B1, that becomes larger then number 1. So this logarithmic will give us a certain positive number. So simply speaking, now this YC position starting from the middle of a channel, now it approaches to the source side. So it is easily understood even in this graphs. So I just drawn here. As you can see here, in this case, I assume a relatively higher bias voltage by our drain to source voltage. In this case, if you just say they decrease in a certain length scale and they decrease the certain length scale, because their deviation from phi s is much higher, of course, compared with this middle of a channel, thus YC value will be shifted to more to this y equal to 0 or source side. So that is not that difficult to understand. The numerical result taken from Professor Tower's book is shown here, and I guess that maybe drain source voltage is about 3 volt. So now drain is much higher compared with this source side, and this red colored line, that is exactly corresponding to the geometric middle point of our transistor. So this is corresponding to y equal to half of L. And where can you find this YC point? Please guess. So our YC point can be found somewhere here in this expression. You can easily understand. So that's the reason why now YC is shown here. The only reason why we have this shifted YC is this impact of high drain voltage. This high drain voltage lays up, so that's the reason why minimum occurs shown here. And anyway, using this YC value, approximate value, now we can use we can try to estimate the value at potential value at YC. This value is interpreted as minimum surface potential, and we will treat it as a corresponding value to maximum EC value seen from our electrons. So that is the maximum height of our channel energy barrier. So that is quite important. So here I added one short notation comment using some approximations. So although I'm writing down using some approximation, that is quite tedious. So please do your own math to derive this expression. This is not quite straightforward, so it requires some lines and pages to perform this kind of manipulation, and it really requires some approximations. Please do it by yourself. Then you will get a certain expression shown here. Also, here I say that this is corresponding to Professor Tower's equation A9.24 following his second edition. But here I added a certain maybe sign because that is not exactly equal to that one. There is some differences in its leading coefficient. So he used 24 for this one, and I think that there is no reason to use 24. It is just an approximation. So whether we say 6 pi or 24, if we say that pi is approximated as number 4. Then we will get number 24. But anyway, please understand, in this case, most important one is not in the second digit or third digit. The problem is to get a certain functional dependence of this maximum potential or minimum potential as a function of other important quantities. So please remember that this is just an approximate solution. But anyway, this gives us the really important understanding. So this is the potential, and this is the one for long channel approximation. So simply speaking, this second term in our right hand side, this is corresponding to the impact of our source terminal and drain terminal. That is reflected by these numbers. Of course, here we have VDS and VDS, and VDS can be found here. Yes, these are impact of our VDS values. Okay, so so please think about this second term. If we go to long channel limit, L becomes much larger. So compared to what? Compared to our lambda value. In this problem, lambda is used as the scale of our analysis. Let's assume that this value becomes positive infinity. So then what happens? It means that here the input argument of our exponential function becomes minus infinity. Simply speaking, this exponential factor becomes just 0. In this case, if our channel length is much longer than our lambda, then there is no impact for our short channel effect. That looks quite reasonable. If we have a long channel device, then there will be almost no change. Why it doesn't have any impact? That is quite easy to understand. So if we have very long channel and say that this is corresponding to our drain side voltage and this is source side voltage, and now if we have such a long channel device, then our potential will diminish here and approach it to phi s, quite a long distance. Also here we have its own decrease behavior. However, that will take a few lambda scale, but that will be anyhow will be gone, and we have plenty of long length scale still corresponding to the full long channel approximation. So the value becomes just phi s. That's the reason why we have just a vanishing short channel effect term. Now think about the other important extreme. Now L becomes more and less compared with L. Now it becomes just orders of lambda, orders of number 1. Now our length scale is more or less comparable. I'm not saying that this is exactly number 1, but just 1, 2, 3, 4. So this exponential function does not vanish at all, and we have to consider this effect. In this case, its contribution can be shown here. Of course, if we have a higher and higher drain bias, this amplitude will become higher and higher. Yes, that is quite easy to understand, because this potential increase given by this source side potential and drain side potential, and having higher VDS is just to raise this right side, drain side potential, so that is quite easy to understand. And here we have a certain coefficient corresponding to still lambda, but if the structure is given, then this is just a constant. So now we can think about still two different extremes. Now length scale is given, and we can think about two different one, 0, and another one is which is a very high one. If we have just number 0, then what will happen? In this case, we will just have a 5e, and here we have nothing, and this becomes just a 5e, so they are just cancelled out each other. So now we have just number 5e minus a times 5s. That is a given number, and importantly, they do not vanish. Even at VDS equal to 0 volt, we still have the value corresponding to 5bi minus a 5s. What is it? It is just nothing but, you have seen it before. So this number 5e minus a times 5s, this is corresponding to the left side, and right side our b1 coefficient, or in this case also c1 coefficient. So now we have still, even at 0 case, we have increase of a minimum potential level. That was called as, in our previous lecture, called as charge sharing effect. So do you remember? Actually, when we have a short channel device, our threshold voltage is changed, usually roll up, and even when we have quite a low drain bias, still we have certain change of potential threshold voltage, and when we apply additionally high drain bias, then we can have even lower threshold voltage. The first one was explained as a charge sharing effect, and second one was called as dibble. And dibble, how can you consider dibble in this case? The dependence of this coefficient on drain voltage can be regarded as dibble. And another one is, even at 0 drain bias, we still have a remaining term corresponding to the B1 coefficient and B2 C1 coefficient. This is corresponding to the charge sharing. Okay, so now let's go to, okay. So now we have this second term corresponding to the effect of source and drain, and when you have a look at this one, this number is just copied into or interpreted as change of our threshold voltage. So we have to make a caution on this conversion. Right now, in this equation A9.24, we are talking about surface potential. Surface potential is the potential at x equal to 0. And now, in this second equation, we are now talking about the threshold voltage. This threshold voltage is the quantity at gate terminal. They are not the same one. So this threshold voltage is assigned to this gate terminal, and surface potential is the one corresponding to this oxide and silicon interface. Of course, there is the conversion rule between our gate voltage and surface potential. What was it? That was change of gate potential is introduced as a change of a surface potential, and there was the conversion rule for these small deviations. That was just a number m. Simply speaking, if we change VGS a little bit, then there is a factor of 1 over m to convert it to the change of surface potential. And you know, in well-designed system, well-designed transistor, this number m should be quite close to just the usual number of 1. That is our goal. That is eventually ideal case. And unfortunately, this is not the case usually. M can be expressed as 3 times Tox WD M, the maximum one. So in this case, more or less its value is in our previous planar MOSFET case, its value is, for well-defined device, it was about 1.3. That means that if this is 1.3, please guess what would be the sub-threshold slope of this device. Let's say your M is 1.3. What does it mean? It means that our SS would be 80 millivolt per decade. Why? M1 is corresponding to number 60 millivolt per decade, and times its M value. 60 times 1.3 gives you 78. So that's the reason why we have 80 millivolt per decade as a typical value of our sub-threshold slope in our previous planar MOSFET case. Now think about our more recent technology called as FinFET or nanosFET. In this case, actually, we have much shorter value for this depletion width. So simply speaking, now for those devices, this value should be regarded as, instead of this depletion width, but should be considered as thickness of silicon, because in this FinFET or nanosFET, the entire silicon region that is fully depleted, so we must take this TS value as the role of WD. So, and nowadays this TS value is quite short. How short is it? It is like 5 nanometer, 6 nanometer, compared with our previous value. So now, so simply speaking, nowadays M value becomes quite close to number 1. So instead of this 60, but now it is easy to see as 80 value, but 60 millivolt per decade can be easily observed in our reported literature. You can see quite a good SS value. But anyway, please note that when we have this equation 8.25, we just made a simple rule making the equivalence between potential change and gate voltage change. So please understand this assumption. And let me just show you typical value in our textbook. In our textbook, we made really crude approximations. That was like 5BI. What is it? This is the built-in potential in our PN junction. It was regarded as 1. And drain voltage also regarded as 1. 5B, yes, this is, well, even in this case, 5B is regarded as 0.5. So 2 times 5B, this is also 1. Is it really 1? Of course, it's not, but we wanted to make it just to make a rule of thumb. So by applying those numbers, so please try to estimate it. 1, 2. So that's the reason why here we have square root 2. And a is 0.2, and here we have 1. Of course, please note that this is not exact. So this is just a typical number. We made a really a crude approximation. And here we have a number that is shown here. 24 is a 24, and WDMT ox, this value is taken as just number 1. Well, that is shown here. So now delta t, this is volt. So here 0.1 means that this is corresponding to 100 millivolt. So we, in this case, we assume that, for this device, I can endure 100 millivolt dibble by this short channel effect. That is the number of 100 millivolt shown here. So, okay, compared with, let me just give you more exact meaning. This delta V is the threshold voltage shift due to what? Due to the short channel effect. So compared with its long channel limit, how much change is allowed? That is the exact number. It is not solely given by Dibble, but combination of Dibble and charge sharing should be considered here. Anyway, let's say that compared with our long channel device, let's say 100 millivolt difference is allowed. That is the maximum I can endure for this short channel device. Let's assume. Is this reasonable? Yes, it is quite reasonable. So as I told you before, the typical value we can endure is more or less a few 10 millivolt. If that happens, then we will be more or less quite happy with this technology. But this value is approached to some large number of 10 millivolt or exceeding 100 millivolt. That is not acceptable at all. So this is quite a reasonable approximation. So now think about this one. Here we have a certain number and certain number, and in order to get this equality, of course this is not exact equality, just a rule of thumb, and we found that the condition for get this equality is about a few times of WD, or 2 times of our lambda scale. That is our result. So here I just draw the limiting case. What is it? It means that if this vertical length scale is lambda, and let's say this lateral length scale is 2 times lambda. In this case, for this 1 to 2 case, then maybe this is the limit of our scaling. If we make an even shorter device for same technology, then this device, this even narrower or even shorter device, will suffer from severe short channel effect. So we cannot use it. However, if we just allow 2 times lambda, then that will be more or less okay to have this length scale. So what we wanted to get is shortest L value. We wanted to reduce shortest L value, because let's say that your minimum length should be this long. Please integrate as many as devices in your technology. Yes. So if your length scale is given, then at most you can integrate 2 devices. But let's assume that in this one-dimensional case, our minimum length scale is given as this short. Then what will happen? You can integrate far more devices into your system, so that is quite much beneficial for your technology. So in various ways, it is good to have this small device. First of all, you can get area efficiency. That's great. At same time, if you can reduce this length scale, since current is more or less follows 1/L factor, so if you can make your channel length shorter than previous technology, then you can also increase your performance can be increased quite easily. So in this case, we prefer to have a shortest device as much as possible, but unfortunately the minimum length scale is actually limited by this vertical length scale. This vertical length scale determines minimum length scale. So our technology development is always try to minimize this vertical length scale. Then if we can reduce it by this short, then maybe that will be the minimum system we can have. This gives us a tremendous implication for our future development. Maybe most of you, if you are interested with the semiconductor device technology, you have heard about the two-dimensional material transistor. Nowadays, there is great research interest to use two-dimensional material for our channel material. Currently, we are using silicon or silicon germanium as a channel material, but instead of that, we wanted to introduce there are some candidate materials and 2D materials. The problem is, or the main idea is, we wanted to reduce the thickness of this system as much as possible. So first thing we can try is just to introduce extremely thin silicon. For example, nowadays we are already achieved the thickness of 5 nanometer, and now some guys are trying to have 4 nanometer thin silicon layer. This is extremely thin compared with our previous case. Previous technology, the number was about 100 nanometer or several 10 nanometer. But now this is reduced to just 5, 4, 3. We are living in that area. Well, that's the reason why we can now live with the length scale about slightly longer than 10 nanometer. For given this technology, for example, let's say this thickness is number 5. Of course, we must consider oxide thickness. So actual number is not exactly corresponding to the silicon thickness, but little bit longer. But anyway, even for considering this oxide thickness, our length scale is more or less, people say that minimum length would be 12 nanometer, or nowadays currently manufacturing numbers is 15 nanometer. We are quite at the extreme of our allowed scaling rule. We are already full use of this scaling property. So the next thing is, well, 15 nanometer, 12 nanometer, It's good. So by introducing this kind of length scale, transistor, of course, it has intrinsic channel. Its length is about 15 nanometer or 16 nanometer, but it is not all of our transistor. In order to make a single transistor, we have to have source and we have to have a drain. So overall length scale becomes about 3 times of this channel length. So currently we have the numbers around 50 nanometer is more or less assigned to a single transistor from the viewpoint of channel direction. But we believe that 50 that is already good, but we wanted to reduce it further and further. Then what is nowadays the most significant barrier for further reducing this overall length scale? Previously, so the total length is the sum of source side length and channel length and also drain side length. Of course, they are symmetric. So people sometimes to reduce source and drain side. So actually that was the main driving force our knob to reduce the length scale. But nowadays we have reduced the source and drain length scale quite aggressively. So there is no room for us to further reduce this length scale. Now it's time to reduce channel length once again. But now think about what happens. If we just keep this silicon thickness and reduce it, then short channel effect will become the showstopper. Oh, I tried to introduce a certain even shorter length. So can you make it or not? Amazingly, we can make it. The fabrication technique can make even shorter length scale. For example, in the last year, in an international conference, Intel published or reported 6 nanometer short channel device. So it is not that difficult for them, not to me, but for them, the guys who are most talented guys, they can fabricate even shorter 6 nanometer technology. But problem is, when they make it, what will happen? Severe short channel effect will occur, so we cannot use it for our logic transistor. So the natural consequence is, okay, the lateral length scale, so reducing the length, L channel length is not that difficult, but in order to get reasonable electrostatic property, actually we reduce this silicon thickness even further, not 5. Our goal now becomes 3, 2, 1. And next question is, can you make 1 nanometer thick silicon, 2 nanometer thick silicon, 3 nanometer thick silicon? Once again, amazingly, we can make it. The problem is, when you make it, its electromobility really drops quite rapidly. It is no longer our silicon, not normal bulk silicon. It has really poor electromobility characteristics. So now you know entire scenario. Scaling is simply given by this vertical thickness. By reducing vertical thickness, we can also reduce the channel length. However, if we reduce the thickness too much, then eventually our electromobility will drop quite rapidly, so we cannot use it as a conventional channel material. However, the promise is, now we have a 2D material. Well, 2D material by its own nature, it is thin. How thin is it? it is about 0.7 nanometer thin. So therefore, even though we introduce 0.7 nanometer thin channel, its mobility is more or less their own mobility. But I have to say that actually they don't have a quite high mobility. So not that good material, but in terms of current condition, but they do not degrade significantly. So therefore, people think that if we go to the extreme case, the real extreme case, when we make the same thickness of 2D material channel and same thickness of silicon channel, then maybe this 2D material channel can outperform this silicon one. That's the reason why tremendous research effort is currently being spent to develop a new technology. So if we ask our engineers to why you are trying to do that, why? If we ask this question again and again, then eventual answer will be this slide. So minimum length is 2 times lambda. Since minimum length scale is 2 times vertical thickness, so that's the reason why we need to find out the way to realize extremely thin channel device. And maybe people think that 2D channel allows us extremely thin channel device. Okay, well, so there are plenty of discussions on this stuff, but let me just move to our main contents, velocity saturation. So before finishing our discussion about this short channel effect, so let me just think about the essential point of our analysis. The essential point of our analysis was this one. We must solve Laplace equation, and from its construction at this top surface and bottom surface, our u function vanishes and u function vanishes. And now we have non-zero value at this one side. Of course, this the opposite side we have a zero value. So simply speaking, this is directly boundary condition just to fix the shape of our solution. Simply speaking, if this is lambda, then our solution will also vanish within scale of lambda. That is the simple way why we have the length scale corresponding to lambda. If we can make a very narrow line, then our solution will follow much smaller lambda scale. So we can reduce or we can confine our source side impact and drain side impact just nearby source and drain, and still we can keep long channel like behavior. This is quite easy understanding on the essential of our problem. Okay, so I think that this short channel effect is really important. So compared with our long channel one, actually there is no long channel device nowadays. It is really difficult to find it. Simply speaking, even engineers cannot generate long channel device. What does it mean? Previously, when we use planar MOSFET, it is really easy to fabricate a long channel device. If you just draw long gate metal, then that becomes long channel device. But nowadays, due to the manufacturing procedure, we need a certain closeness between source and drain, because usually what we do is here we have a source and drain. For some cases, nowadays for state-of-the-art devices, our silicon are just exposed to the air. There is nothing, 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 and they are for a while, they are just hangover. So if we have quite a long channel device, actually they will make this kind of bending and eventually failure to get proper structure. So nowadays it is almost impossible to get the long channel device. So the length scale is given as a certain number. If we are talking about digital system, and we are currently talking about digital system, it's completely okay. Nobody uses long channel device. But problem is sometimes we need to implement also analog device. In the case of an analog device, actually our state-of-the-art device is not that much suitable because they cannot provide a long channel device. And in analog scene, actually long channel device gives us plenty of advantages. So therefore, well, our discussion is more or less for digital one, VLSI, but we have to understand it's not. Nowadays there is no one fit to all device. If we have one type of device, it can be used there and there. Actually, previously in the case of a planar MOSFET, the planar MOSFET was the tool, the device fit to every requirement. However, nowadays our devices are separated and we can have many different applications, and depending on applications, the best one are different. Okay, so now that is the real end of our short channel effect discussion, and now let's move on to the velocity saturation. So here, currently you have two different devices. One is long channel device, another one is a short channel device. I don't remember exact length scale. Maybe it was, I remember 50 nanometer something. So now you have, for each device, you have two different curves. Of course, red one and blue one. And let me just explain what is the difference between red one and blue one. Red one is obtained by considering only mobility due to gate voltage, or mobility reduction due to gate voltage, or vertical electric field. So, well, maybe, oh, this is not the one. Oh, yes. So we have seen this curve. As a function of effective field, the mobility follows universal dependence. So do you remember? This is the effective mobility of a silicon channel, and here we have effective mobility, and maybe you remember that this effective mobility has some factors like oxide field and silicon field, and there is a certain numbers corresponding to a half or 1/3 depending on polarity. And MOSFET and PMOSFET, they have different numbers. But anyway, this effect was considered in this blue curve. Oh, sorry. This is red curve. And then what is this blue curve? Blue curve shows a little bit degrade of our current conduction compared with this one. Oh, we have already considered realistic effect of mobility degradation due to the high gate bias. But what is the additional physical mechanism additionally considered in this blue curve is now velocity saturation. Velocity saturation simply means that people made this kind of experiment. So make a register, for example, let's say that there is a certain distance and that is grounded, and apply certain voltage, and let's say that this is a length scale L and V. In this case, well, this is the potential difference becomes just V and length is L, so we can think that the average electric field inside this simple resistor, it is not a transistor, it is just uniformly doped resistor, then electric field would be V divided by L. That will be the value, and they just increase voltage. Increasing voltage is corresponding to increasing electric field, and they measure the current. What is your expectation? Well, if you apply 1 volt, let's say that you have, for example, 1 ampere. If it follows the linear relation, if you apply 10 volt, maybe you will get 10 amp. 100 volt, 100 amp. This is the linear relation. But you feel that something wrong. Then if we apply 1 kilovolt, 1 megavolt, 1 gigavolt, what will happen to this guy? It can give us 1 giga amp for this small resistor. Maybe not. So there will be certain deviation from this ideal IV characteristics, and people have found that experimentally. Well, if we, maybe, oh yes. So if we increase electric field higher and higher, then we can expect higher and higher electron velocity. So think about this one. Here we have electric field corresponding to 1 kilovolt per centimeter, and this is corresponding to 10 kilovolt per centimeter. Then since electric field becomes 10 times higher, if we just follow linear relationship, then speed or velocity of our electrons will become also 10 times faster, because electron velocity follows mobility times electric field. That was the assumption we have made up to now. So 10 times higher mobility, 10 times higher electric field gives us 10 times higher velocity. Then how does it look like? Please have a look at this actual graph. This is the one corresponding to 1 kilovolt per centimeter. And if it really follows the linear relationship, our next velocity at 10 kilovolt per centimeter should be here. Simply speaking, we must have this straight line for our velocity versus electric field curve. But what happens in the realistic case, experimental data? As you can see here, if we have sufficiently high electric field, then the velocity does not increase any further, and it is approaching to a certain value. So this phenomenon is called as velocity saturation. So now let's say that you ride a horse and you just punch it it quite occasionally. Hey, then it goes faster, faster. Then let's assume that you now 1,000 times faster hitting it. Then do you expect 1,000 times faster horse by acting this increased hitting frequency? It's not. Simply speaking, in this case, our electrons are at the end of its available speed. This electron gas cannot give us faster speed from its ordinary operation. So this is corresponding to our silicon material, and this value is typically given as 10 to the 7 centimeter per second. This number is almost given for our silicon material. Of course, this value is not universal. For example, if we consider different materials, certain materials have higher saturation velocity and certain materials have lower saturation velocity. Unfortunately, 2D materials are known to have much lower saturation velocity. So just half or 1/3 of this silicon value. And which one has higher numbers? The well-known numbers, like well-known materials, are 3,5 compound semiconductors. They are known to have higher saturation velocity. It really depends on their band structure or something like that. So anyway, for our silicon material, it is about 10 to the 7 per 7 second per centimeter per second. You must remember this order. It's not like 10 to the 6. It's not like 10 to the 8. 10 to the 7 centimeter per second. And this number is more or less corresponding to the velocity, average velocity of our summer excitation. So, you know, this electron gas have random velocity due to the given temperature. At 300 Kelvin, of course, it has a certain summer velocity, and this is 10 to the 7 is more or less similar to the summer velocity at 300 Kelvin. This is not there is no physical rule to be sure, but happen to be they are in the same range. Okay. Simply speaking, now we have, let's come back. Now we have these two curves. This blue curve is obtained by considering velocity saturation effect. In the case of our long channel device, even though we have considered velocity saturation effect, yes, it is reduced, current is reduced a little bit, but as you can see, it's not that much drastic. But please have a look at our short channel device. What happens? This was the value without velocity saturation, and this is the value with velocity saturation. So you can see that there is a huge reduction of our current, maximum current, almost 3 times smaller than the previous case. So that becomes really a limiting factor for our own current. So that is quite bad news. So although that is bad news, anyhow we have to consider this effect not to overestimate the gain we will get for short channel device. Even though we have made a short channel device, but the real performance is a little bit lower or significantly lower than we may expect from extrapolation from long channel regimen. So we must consider this velocity saturation. Okay, so let's continue our discussion on next Monday.